right, good morning. How you guys doing? Good, good. See, we're missing a few people. I guess maybe we'll get them online. We'll see. All right. Today I want to pick up where we left off with coagulation, and then essentially cover flocculation. Flocculation itself is not a particularly difficult or challenging process. There are several equations that will go into it, so to give us some way of knowing how many particles do we have that are going to stick together compared to what we started with. That'll give us some information about how big the particles are going to be, but ultimately it's just going to be a simple mass balance for flocculation chambers. So last time we were talking about the electrical double layer, or EDL, in the context of destabilizing particles, giving them a favorable environment to stick together and to essentially grow in size with a flocculation process. So coagulation would be the process of destabilizing them, maybe shrinking this electrical double layer. And then flocculation is then giving them the chance to stick together once they've been destabilized. I briefly ran through these little plots here. Essentially, they're showing you can change the distance of the electrical double layer. The ones on the left are showing that distance in nanometers. And so up at 50, and then on the y-axis here, they're measuring the potential, which is the electric field. So how far into the water, away from a surface, does the electric field travel or exist? And you can see that that's going to change that the strength, so the strength being the y-axis, so the strength of the field. Will decrease as you go further and further away. And that will change if you add different types of salts or different amounts of salt. So the top one up here is showing different amounts. If you add 60 milligrams per liter of sodium chloride, you've got a strong electrical double layer all the way out past 10 nanometers. It's a very strong field. And if you take maybe a weaker field, something around 20 millivolts, it's probably still enough charge or field strength to keep particles separate. That's all the way out to 20 nanometers. So if that was our condition, that you had to drop below some field strength like that, then what you can see then is if you add more salt, then that the distance at which that stabilizing force acts shrinks, right? So you can get it down to a little bit below 10 nanometers with 600 milligrams per liter. And then you can get it down to maybe like 3 or 4 nanometers with 6,000 milligrams per liter. And so it's a combination of that field strength. If there's like no strength at all, then it's not really going to have a force to keep particles apart. If it's a very short range field, so it's been compressed a lot, then the van der Waals forces will overcome them. And that'll happen somewhere in this range, about 5-6 nanometers. That's when you start having significant competition between the two. So all that to say, you add more salt, you get destabilized particles, and therefore you are able to cause them to stick together. The other thing, that's where this graph came into play, is we can take a look at what type of salt we're using. So over here, it was just all sodium chloride. Down here, we're taking a look at the charge, Z. So +1 here, that would be sodium. +2, that would be something like calcium. And then +3 down here, that would be something like aluminum. And you can see the same effect here where sodium doesn't do a particularly good job shrinking that double layer, it, you have a strong field strength all the way out near 20, and this is all with the same amount of sodium, calcium, or aluminum there, or 1+, 2+, 3+ ions. And just tracking the difference by changing the charge there, you can see that aluminum is much more effective on a per mass basis or per molar basis. Okay, and we understand that because we know that our ionic strength is really what's causing this phenomenon to change, and that depends on the charge squared. So if ionic strength is dictating the stability, because ionic strength is essentially how many charges are available, we can solve for ionic strength for the different species and recognize that the same concentration of aluminum is a lot higher ionic strength than sodium, right? So if we were to take a look at, yeah.
Is that distance on the bottom the distance
I only heard part of that. So the distance on the bottom is at what?
like so for on the graph the distance that mark there is
Yeah.
that based on that picture you just on of like all the ions?
Yeah. So, okay, so it's a good question. So we can take a look at this distance here, and then compare that to the previous plot. That would be a distance like this. So that would be the same distance here as on that graph. So you could then say, well, you're detecting a significant electric field out some distance away from this particle, and that electric field is essentially, you're sensing it based on that double layer distance. So however far this double layer goes out into solution, and it might help looking at this diagram to imagine that instead of this entire circle being the atom that's giving the charge, imagine that the atom that's giving that charge is actually a tiny little atom inside there, and it has a charge kind of zone. And then you can also imagine that, so there's extra space there. And then also imagine that charge zone might increase if there's just few ions in the whole solution. It's having a greater effect. You could also just imagine that these are spaced a little bit more, but those two concepts combined hopefully gives you an appreciation of that these atoms are not just going to be next to each other necessarily, unless you have a whole bunch of them, and then it just makes it makes sense just based on the gradients and all that. So yeah, it's a good question. That's the distance that we're talking about right here. Okay, so just a quick reminder about ionic strength. I think you should have seen this plenty before, but if we were to solve for the ionic strength for sodium chloride, this would be very simple. It would be 1/2 times the concentration, the molar concentration of Na plus times that +1 charge squared plus the concentration of Cl minus times the -1 charge squared. That would be your ionic strength. Whereas if you had, let's say, aluminum sulfate or alum, then you would have to solve and figure out, okay, well, for every time I dissolve one of these, you get, so 1 mole of alum gives you 2 moles of aluminum ions. 1 mole of alum gives you 3 moles of sulfate ions. And so then you'd have to solve for your Al3 plus concentration based on that. You'd also need your sulfate concentration, SO4 minus. And in the brackets here, this is molar units. We have solved for, the fact that 1 mole of alum went to 2 moles of Al3 plus. That all goes into the calculation before this point. And then you would put these in and say your ionic strength is equal to 1/2 times that AL 3 plus times 3 squared plus your sulfate concentration times -2 squared, and that would be your ionic strength, is the sum of those two for that equation. So keep that in mind. You may have to use that. Should just be a quick reminder there, right? You've seen that before. Okay, so have an example here for ionic strength. I don't think you guys really need it, but if you are wanting some practice, there's an example problem you can come back and do on your own. So with that, I want to get into flocculation, and if you guys want, I can run through that problem with you. I'll come back to that if you want me to, so do let me know. For the flocculation, essentially the process, what we're going to do is after we destabilize, so we've added some coagulant typically, that's going to be that coagulation dosing, which is typically mentioned last time, a small box. It's very well mixed, water's coming in, water's going out, and essentially we're just injecting the coagulant and dosing it that way. So the coagulation chamber is the only purpose is to mix it, and so add the chemical and mix them together and then send it along. So coagulation is very simple. It's a very small reactor, very high mixing rate. That's basically all it is. For the flocculation chamber, we want something a lot slower. Now that the coagulant has been added and is well mixed, we want to give it time to act. So in order to allow the particles to meet each other and collide, form new particles, we want to give gentle mixing. Again, we'll typically use a CSTR. Of course, we could use a batch reactor for this as well, if we wanted to do just a batch at a time. But typically we'll use a CSTR, and it'll be gentle mixing, typically a larger chamber. We do not want turbulence. We just want pretty much laminar flow, or probably laminar flow with gradients of different speeds. So there's that gentle mixing, but there's no shear forces to strip the particles back apart. The goal is to reduce the number concentration over time. So not that we're removing any particles here, but whenever they meet and stick together, we're going to consider that one new particle from two old particles, right? So then if we reduce the number of particles, that just means they're getting bigger, because now the bigger particle is labeled as one particle. So we go from a particle here and a particle here, and that goes to one particle there. So we went from 2 to 1 by that definition. So when we solve these problems, what we're going to do is look at the kinetics of removing particles over time, or reducing the number of particles over time. So N is that number concentration of particles. We could write it as particles per liter or cubic meter, whatever we want to use. So that's going to be part of our assumptions, that each particle is discrete, and then once they meet another one, they form one new discrete particle that takes up twice the volume of the original particle. So the volume's not changing per particle. They're just sticking together. We're going to also assume that for purposes of our calculations, that somehow these two spheres join to make one new sphere. Okay, so we're just going to stick with keeping a simple case, and it turns out those assumptions are pretty useful in general. It's not that's not descriptive of all of reality, but like I mentioned last time, there's different types of sedimentation we can take a look at, and that would be one thing that could change it. So the question becomes, okay, well, at what rate are these particles going to meet, and at what rate are we going to have the reduction in number of particles? So that's going to be a k value, so a rate constant for the system, and we're going to need to solve that based on some of the parameters of the system. And you can realize, if you think about it, the speed at which you're stirring is going to matter, right? Assuming we're in some realm of stirring that's not too vigorous where it's going to break the particles apart. So assuming it's in a decent speed or decent mixing intensity, the faster it goes without shearing particles apart, the quicker they'll meet. So the mixing intensity has something to do with it. There's going to be that destabilization factor is going to be a part of it, particle size, all of these things. So first we'll want to take a look at the mixing conditions. And we have a term called mixing intensity, or G. So mixing intensity is going to be essentially looking at the velocity gradient of water passing across a surface, or a surface passing through water. We can define this as, if we have some surface here, and next to the surface we have water moving with some velocity, it's slowed down because of drag forces. So the water right next to the surface is going to be slower than water moving a little bit further from the surface. And we'll have some gradient that we could draw like that. So you can imagine that by me stirring my bottle around, the speed at which water is flowing next to the surface, it right up very, very close to the surface is going to be slower. You can also imagine this effect on a paddle wheel or a propeller, mixing propeller, something like that. So then we can draw a line for this gradient. See if I can draw a better line. So this gradient line then, the slope of that is what we call G. So that's our mixing intensity. And we can take a look at this and say, okay, well, this gradient here, what this is describing is we have some distance, we'll say y, and we have a velocity, some velocity term v. So we could say, well, this mixing intensity here, if I get this right, we could say dv dy equals g. So the differential of velocity per distance away from that. And then if we take a look at the units, this is going to be something like meters per second per meter, and that just becomes second to the minus 1. Okay, so that's kind of where the units come from for this term. The units are per second for mixing intensity. That's kind of the conceptualization of what we mean by the mixing intensity, how we might define it. I just wanted to show that, demonstrate that. We're not really going to deal too much otherwise with the derivation of this term, but I wanted to kind of show what it means mathematically and conceptually. So we have a definition we can use for mixing intensity. That is this equation here. G is equal to the square root of the power that we put into the mixing. So we're adding some power in watts to a stir bar or a stirrer of some sort, divided by the dynamic viscosity of water times the volume of the basin that we're stirring in. So if you put a lot of power into a 1 liter reactor, you can have a very high mixing intensity. If you put that same amount of energy into a swimming pool, it's not going to result in much mixing in the swimming pool, right? So it's a very understandable why the volume matters, obvious why the power matters. And you can also think of if you were to shake a jar of honey compared to water, obviously you're going to have less mixing in the honey as well. So makes sense that each of those terms are going to affect this term, this mixing intensity concept. So, and keep in mind this is that VB here. That's the volume of the chamber or the basin. That's the B. And the units, we need, if we're going to use watts, which we will, then we need the dynamic viscosity in kilograms per meter per second, because watts is a meters and seconds and kilograms type of unit. And that means our volume also needs to be in cubic meters. Okay, so on to flocculation then. When we have a collision, I mentioned this earlier, but essentially what we're going to do is we're going to have two particles. They're going to collide and form one new particle. So in order to consider how this is going to act or how we're going to measure it mathematically, let's consider two volumes. And so rather than particles here, I'm going to say each of these circles is like 1 cubic meter of volume, or one amount of volume, something like that. 1 liter, 1 milliliter, something. And we have some number of particles inside here. Okay, so there's, I think, 11 particles there, and they're all floating around. We destabilize them, we send them through the process, and then as they go, maybe most of them stick together. Let's say in this first case, let's say they all stick together. So now we have one particle. And I made 11 little dots there, some overlapping, and that's our new particle. Okay, so we went from an initial n equals 11 particles per volume and now we have just 1 particles per volume. So you can see what I'm showing here is we take the some set volume, and then we're changing the number of particles by causing them to stick together. That is our dn dt. So when we solve for some system and we have, we start with dn dt, let's say in a batch reactor, we know that our n over n naught is equal to e to the minus kt. The meaning of the n over n naught directly relates to the size of the particles here, right? If we know something about the size of the initial particles, then based on our n over n naught, we know something about the size of the final particles, okay? So there's a lot we can do with this mass balance just because we're assuming that the particles are discrete and we have no change in volume or density or anything like that. So a couple assumptions I should probably put here. Again, we have the discrete particles. Those new particles are going to have a volume equal to the sum of the volumes of the initial ones. I'm just going to say the sum of old particles. So the net particle volume is not changing in the system. They're just the number of particles that we define, right? Okay. So in this case that I drew here, we see that if we say n naught over n, which is backwards from the n over n naught, it's inverted. This is equal to 11 in this case, right? Because we said we had 11 in the first place. Now we have 1. So n naught over n is equal to 11. Of course, you could say n over n naught is equal to 1 over 11. That's not quite as useful because n naught over n is telling us how many of the initial particles are in each of the final particles. So we have, based on that math there, we can say that there are 11 initial particles in every aggregate. And when I say aggregate, what I'm meaning is this new particle. Okay, so should hopefully make sense there. It's I'm being very elaborate here because when we solve problems, it does come back to exactly this, and if you miss this part, you'll be confused about what you're trying to solve for. Okay, or how to get there with a mass balance. Okay, so let's talk a little bit about the rate constant K. And remember, if we have some mass balance, right, we have accumulation. It's going to be equal to the in minus out plus whatever reaction's happening. If we do this in a batch container, like my water bottle, then there's no inputs or outputs. Typically, however, we'll do this in a CSDR. So you should be able to do both, of course, but typically we'll see this as a steady state. We're going to have Q n naught minus Qn. And then this is going to be a negative, it's a decay reaction if they're sticking together rather than breaking apart. So then we'll have minus VKN. Now I put this here as VKN, first order, because we know based on the simple principle that particles sticking together, it depends on how many particles are in there. If there's 2 particles in my entire water bottle, they're not likely to meet each other, so the rate's going to be pretty slow. If there's 2 billion particles in here, there's going to be a fair number of collisions happening. So the rate is going to depend on the number that are in there. So that's why we've got this at first order. That's why it's n to the power of 1 here. Okay, so that's going to be our form for most of these problems, unless we happen to be doing it in a batch. So we need to know this K, because if we know that K, the only other things here are Q, which is pretty simple, volume, pretty simple, and then the number, right? So that number is going to give us information about how big the particles are going to be, and then if we can learn something about the size of the new particles, then we know how quickly they're going to settle. Okay, so all of this really aims at understanding, are these particles going to be sufficiently large to settle in our sedimentation process like we want? Okay, because we remember back to sedimentation, the goal is to use gravity for what we can, then go through this coagulation flocculation process and do sedimentation again. So all of this is geared towards causing the destabilization, having them stick together, and then form these larger particles that we can settle. So we need to know how long that's going to take, how big the particles are going to get, all of that. So going back to K, need to find K. Well, we have an equation, and it's going to relate to this term, which is collision efficiency. Collision efficiency, that's going to be essentially some metric of how destabilized they are. Are they going to form a new particle every time 2 particles meet, or only half the time? So this collision efficiency, this is a factor that goes from 0 to 1. At 0, they are completely stable particles. They're never going to form a new particle. So this would be completely stable. Whereas 1 is completely destabilized. So every time two particles meet, it's going to form a new particle. So if this alpha equals 0.5, 50% of collisions result in a new particle. Okay. Okay, so that's the first term there. We don't really have a good way of identifying this collision efficiency aside from a problem being maybe you're given it, maybe you're solving for it, something. We don't have a good way of saying, oh, if the ionic strength is this, then the collision efficiency is that. And there's other factors that can destabilize particles we'll talk about in a little way. Okay, so that's the first term. Then we have a factor of 4 here, so 4 times that collision efficiency. Then we have this omega, and really that's the only other strange thing here. We have G, which we talked about a minute ago, so we know we have a formula for that, and that term is in per seconds. So that's really where our units are coming from here. This collision efficiency is unitless. It's just a fraction. What fraction of collisions yields a new particle, and then pi on the bottom here. So this omega term is what we call the Flock volume. The Flock volume is a unitless term, but perhaps more accurately, it's actually volume per volume. So it's technically volume of particles per volume of solution. Now, I say it's unitless. We need it to be unitless for the math to make sense here with a k of per time. So in order to achieve that per time, we need that Flock volume to be unitless. So that means we cannot do some like milliliters per cubic meter. That would not be okay. We have to have, typically we'll solve in cubic meters per cubic meters. That way we get units. Okay, so what is this term? I say Flock volume. When I describe it as the volume of particles per volume of water, hopefully that will help a little bit. The way we can define it is essentially the volume of a sphere, pi times diameter cubed divided by 6. So the volume of a sphere, or volume of a particle, we'll say dP equals pi dP cubed over 6. That's for one particle. And then we need to multiply that by the number of particles we have and divide by a given volume that we have those particles in, right? So that's where the n comes in. So that's for, let's say that's one particle. Then our omega then is Vp times the number of particles per volume. Okay, so that's where this term is coming from. And the thing here is n naught, we're often going to have to convert the units. Probably diameter particle as well. So n naught is often maybe number per liter, and then diameter of the particle might be like micrometers. So we certainly have some unit conversions to do to make sure that we have, instead of liters, we get cubic meters. I'm going to highlight this differently. So we need to convert both essentially to meters, or cubic meters, rather. that make sense? Okay, so then coming back to our rate constant, the rate constant is equal to the collision efficiency times 4 times the volume that is of the liquid that's occupied by particles. That's our flock volume. So in my, 300 milliliters here, maybe 1 milliliter of that is particles. That would be a lot. That's 1 over 300 is then the flock volume. So this flock volume, omega, you're going to see it often as a very small number, a very small fraction. It's going to be like 5 times 10 to the minus fifth, because clearly if I have some particles in here, it's a very small, like just by definition, it would be a sludge or a solid if that was near 1. Okay, then it's also relating to the mixing intensity there, and divided by pi. So that'll give us a rate constant in per seconds. Good on that? All right. Okay, so I think this is just basically all of that written out again, so you have it nice and clearly. Okay, so let's use it, solve a problem. We have example 6.2 from our book, silt flocculation before sedimentation. It says to improve their settling, the 0.01 millimeter silt particles in some other example. We've got, this was a sedimentation example. I put on the last section of slides, but I passed through it. But if we take a look, here are the parameters that we had from that last problem. So they are passed through one of 2 side-by-side, well-mixed flocculation chambers. Chambers are cubic, with each dimension being 3.5 meters. They are mixed with paddle mixers that input 2.5 kilowatts of power into the water in each chamber. The water entering the flocculation chamber contains 10 to the 5th particles per milliliter. Question is, what is the average diameter of aggregates leaving the flocculation chambers? So, take a few minutes, work on this, see what you can do. Work with each other if you'd like. After maybe 5 minutes or so, I will step in and make a few comments about how to start. But I'll encourage you right now to start by drawing the system, start by writing out a mass balance, or your best guess at what mass balance you're going to need, and then identifying really what are you trying to get at, how do you get there. So, sorry. You're asking about the what this number is? That's mu. It's mu. Let me write it down on here. And I do apologize. I didn't realize that gets cut off here on the system. Yeah. And mu is the dynamic viscosity of water. Okay, so I drew out a schematic. Hopefully you guys did the same. Probably worth checking with you before you get too much further, because there's several mistakes you could make in the setup, especially if you're thinking too far ahead at what you need without first drawing and considering what you have in terms of the system. So we had a flow rate, and that was split between two identical reactors in parallel. And so that means we're splitting the flow in half. Half of the flow is going one way, half the other way. So each reactor is getting 1.5 MGD instead of 3 MGD. And then drawing the volume and solving for the volume is 3.5 meters. That's cubed, so that's 3.5 cubed rather than just 3.5 cubic meters, right? So make sure you got those points taken care of as you go forward. So continue working on it. I'll start solving for the G, and then I'll start setting up some of it, letting you work, and then I'll talk with you again in a minute. Okay, so based on what we talked about earlier, that n naught over n is going to be pretty helpful knowing how many initial particles are there per final particle. So I would recommend taking your mass balance, which is going to be for CSTR, first order decay, 0 equals Qn naught minus Qn minus Vkn. That's our form of it. And work that to solve for n naught over n. We've done n over n naught before, so this time we would just essentially take that solution and invert it, or just solve from the first place for n naught divided by n. So if you do that, you should get 1 plus theta k. It's a pretty simple term for n naught over n. So then that begs the question, what is k? And you can go from there. Okay, so I'm going to pause you here for a moment. I've got a very simple Kahoot quiz. Want you to give me the answer for G, and then the other answer should be obvious. So give me your solution for G as the first question. You'll have a moment. So make sure you're comfortable with your calculation for G and the problem. Sign in here. So I'm seeing 5 viewers online. It's been between 4 and 5 most of the class, so unless my mom is watching or something. All right. Expecting 11 here, but maybe somebody's got not paying attention. Okay, there we go. All right. And then I'll go through the solution and the numbers with you in a moment. Should have time. So what was your answer for G? The closest one? Okay, so several of you picked the 1.28, or excuse me, 128 per second. I think you took the volume of the chamber and divided it by 2, perhaps. I think maybe that's what got you there. But you didn't need to divide that volume of the chamber by 2. So we'll take a look at that in a moment. Okay, second question. Would flocculation happen faster in water or honey if viscosity was the only difference? Okay, so we've got 1 troll and 10 correct people. So as I said earlier, honey is very viscous, and if you're mixing it, you wouldn't be able to. You'd have to put a lot of power in to get the same stirring action. So it's going to be water where flocculation can happen faster. Given that was just 2 questions, I'm not really going to. I'm just going to treat it like the little attendance, yes or no. Were you here? Did you participate? So don't worry yourself over the grade about that. Okay, so in terms of G, so if we do solve that square root of P divided by mu volume of the basin, what we have is the power is in 2.5 kilowatts. We need it in watts, so that's 2,500 watts. So that'll be the square root of 2,500 divided by the viscosity, 0.001145, times the volume of the basin, which is 42.875. Probably be good to put in the units here. This is watts. This guy is kilograms per meter second, and this guy is in cubic meters. So if you solve that, you should get should hopefully be getting with that that 226 number. So That's how I solved it in Excel here. That's what that number was coming from. Does that make sense? Were there any issues with that? Okay. All right. So the next part of the question, or the next component, I guess, we'll put this in here, 226. We're taking a look at the mass balance, and we want to know K. So we go through and we essentially solve part of our mass balance. We get to 1 plus theta K is kind of what we need. So we can solve theta, that's V over Q. That should be 652.6 seconds. Then to get K, we need omega. Omega, that's pi times the diameter of particle cubed times the number concentration of those initial particles. I guess we could use the diameter of the final particles and the concentration of the final particles. That would work too, because we're assuming the volume doesn't change before or after. But this is the standard way. We usually know more about the initial state than the final state. That divided by 6. So if we take a look at that calculation for omega, first of all, we have to take that diameter of the particle and convert it from millimeters to meters. It was 0.01 millimeters. So I took that and said 0.01 divided by 1,000 to go from millimeters to meters. So that gives us essentially 1 times 10 to the minus 5th meters. Then we had the initial concentration of particles, and that was in per milliliters, particles per milliliters here. And so in order to get that to particles per cubic meter, if you imagine that difference, the number of particles in 1 milliliter, small volume, and that was 10 to the 5th particles. Well, we're going to have to multiply that by 1 million to go up from a milliliter to a liter. That's a multiplier of 1,000. And then from 1 liter to 1 cubic meter, it's another 1,000 multiplier. And that gets us to a net of 1 times 10 to the 11th particles per cubic meter. Okay, so that gives us, once we put in those numbers into the omega, we have this 5.23 times 10 to the minus 5th. That's the fraction in every cubic meter. That's the portion of that cubic meter that is occupied by particles. Okay, so then we had that guy that was 5.24 times 10 to the minus 5th. We have K then we can solve because we have G, we have that. One final thing here is we need to know the collision efficiency, and that was given to us when it said the particles are completely destabilized. So when it says completely destabilized, we know that that collision efficiency is 1. Okay, with that, then we can put in those numbers and get K. So K is going to be 0.015 per second. Okay. Finally, we can get our n naught over n by putting this in, and that's going to give us just about 11, so 10.81 initial particles in every final particle. Okay, so that gets us very close to the answer, but perhaps what we should have started the problem with, and I guess since I knew where we were going, I knew what we were looking for or how to get there, but a good place to start the problem really would have been to say, okay, I have, what I'm looking for is the diameter of an aggregate, right? So I need diameter of the aggregate. So that would have been a good thing to just start the whole problem with after drawing your diagram there. Well, what we can know something about is the volume of an aggregate. We know that volume of one aggregate is going to be equal to the volume of one particle times n naught over n, right? That's the number of particles, number of the initial particles in every aggregate. Oops. I just erased something. Hang on. Okay. So we could write that as n naught over n, or we could just go ahead and say that's 10.81, now that we know. So with that, we can solve and say, oh, okay, well, if we know the volumes here, we can also, instead of say volume, we can convert to diameter and say, the volume of a sphere, again, assuming these are spherical, that is going to be our pi dp cubed, so this time d aggregate, divided by 6. And so we can set that equal to the term on the right and say, well, that's going to be equal to the pi dp cubed divided by 6 times 10.81. And that in that manner, we can then solve for the diameter of the aggregate. Because we know something about the diameter of the particle, we now know how many particles are in each aggregate, and we can solve the final solution, diameter of the aggregate, and come up with an answer there. Okay. So what I'm going to do then is take this to the side. Sorry about that taskbar there. Okay, so we're just going to solve the aggregate. So that's going to be equal to, you know what, let's do this. So the 6's will cancel. So we're going to say the aggregate is going to be, the pi's are going to cancel, the 6's are going to cancel. That's going to be, say d aggregate cubed is equal to dp cubed. No, we'll just do this. dp cubed times 10.81 to the 1/3. Yeah, that's all it is. Okay. So then our answer here in meters is 2.21 times 10 to the minus 5th. If we wanted that in millimeters, multiply that by 1,000, and we get 0.022 millimeters. Okay. Does that process make sense? Kind of involved, but in terms of the mass balance, it wasn't too different than what we've seen. Just lots of units, lots of things to solve for. Okay, so that's all for today. Next time we'll get into combining sequential reactors and get into granular filtration.